Cancer is the second largest cause of death in the United States, with diagnosis rates being as high as 39.6% of the U.S. population. At late stages, tumors grow beyond their origins, making surgery ineffective and necessitating non-selective treatments like chemotherapy, which flood large areas of the body with toxins. Achieving a more controlled eradication requires a molecular sensor that is selectively active against cancer cells. Recent work has identified certain antimicrobial peptides, or AMPs, as selectively folding near cancer cells due to electrostatic interactions with the anionic membranes. Research is mostly limited to the alpha-helical form, but the alternate beta-hairpin form theoretically requires less than 50% as much local concentration for disruption and exhibits greater mutation resistance due to the stability of the anti-parallel strands, making it better suited for rational modification. I studied SVS1, a beta-hairpin 18 amino acid synthetic peptide with amphiphilic phases. I hypothesized that stabilization of the disulfide bonds, which would trigger folding before membrane contact, would allow the hydrophobic portion to engage with the inner lipid portions. To test this, I synthesized an analog, SVS-Bedan, whose fluorescence is sensitive to hydrophobicity. Equilibrium and time-resolved fluorescence verified folding in the presence of charged cancer-like vesicles and random coil conformation otherwise. I then used light scattering to determine aggregation and insertion efficacy, observing that SVS1 exhibited a significantly lower wave number than control, indicating decreased aggregation and increased alignment along the principal beam axis, suggesting consistent insertion. Finally, to understand insertion dynamics, I ran a molecular dynamics simulation of the peptide membrane system in GROMACS, testing with multiple surface tensions. Baleen contact histograms revealed that the N-terminus inserted first and eventually reached the hydrophobic tails of the bilayer, with subsequent lipid displacement. This demonstrates the viability of beta-hairpin SVS1 in cancer sensing and indicates broad potential for peptide-based therapies. Aside from direct membrane disruption, my observations suggest that one could ligate molecules to the N-terminus to achieve controlled drug delivery, or even embed manufactured antigens in membranes to trigger an immune response to cancer cells.